So this is Generalized Linear Models with Examples in R, that book there. And we are on question 3.24. Yeah, so we'll just go piece by piece here. So we're going to look at a data set. Make sure to tell us that it's an artificial data set. We'll see why here in a minute. And it's called triangle. Okay, so we'll come to each question as we come to it. But let's look at the data here. So we need to install packages, load GLM's data, call up the data set triangle, and I'm just calling it D, and we'll look at the first few rows of that. Yeah, you know what? I should have just done this. Give me a second. Okay, so this is the first few rows of it. So we have y, x1, x2, and what this is it's two sides of a triangle, the non-hypotenuse sides, and the hypotenuse. So y is the hypotenuse here. Okay, and so how is this made? So presumably they just picked some random x1 and x2. Squared them and took the square root by Pythagoras' theorem to get y. And then later we learned that they also added some random noise to y. So it's not a perfect fit, but it's roughly fit. Okay, so part one here is we need to fit linear regression model of y equals x1 plus x2. Show that the interaction term is not necessary. Okay, so I have a model that's just like they said. And then I have modified the model by using, instead of a plus, a multiply. So this will give us both additive terms as well as the interaction term. And then we'll look at the summary output, and then we'll also compare the two models with ANOVA. Okay, so we run that. So the first model, without the interaction, we see that both x's are significant. And then if we go down to the interaction model, we again see that both x's are significant, but the interaction is, not very compelling across the board. And if we look at the ANOVA for the two, we see that adding the interaction here with model 2, it really does not significantly improve the fit. Okay, so this is all pretty, decent evidence that the interaction term is not necessary. Okay. So now we're supposed to use some diagnostics for the model. So again, I'm just using the plot function, but you could get into as much depth as you wanted here. But what we will basically see is that the model does okay. It's not terrible. Okay, so good enough. All right. And so now we need to interpret the fitted model. Again, so this question comes up in a lot of these questions here. And it's almost a tautology, because I think that the answer that they're looking for is y is a linear function of x1 and x2. It's x, so anyway, without an interaction term. But that's, you can just read that off from the model, but I think that's the answer that they're looking for here. So there you go. Okay, now we're on part 4, and this is where it tells us a little bit more about how the data was generated. So it says that the data were actually generated by this, okay? Mu equals the square root of x1 plus x2, or square x1 squared plus x2 squared. And so what we basically have is where mu is not the hypotenuse, it's the squared hypotenuse. Or no, that is the hypotenuse. Okay. And so what they did was, to make y instead of mu, is they added some randomness to make y. Okay, so what does this lesson, or what lesson does this demonstrate? Okay, I'm not sure, but I think that what this demonstrates here is, so here we have the data generating process. All right, here, okay, and yet the model that we're fitting is this. Okay, now, so the model that we have does not represent, it is, the model that we have is not the data generating process, right? If it was the data generated process, then it would be the square root of, this squared plus this squared, all right? And yet, we get a decent fit for the data, right? And so I think that the lesson is that our models do not necessarily need to reflect the data generating process in order to be fit to the model, and further to fit well to fit the data, or to fit well to the data. Okay, so we can have a good fit of our model to the data, but that does not necessarily mean that the model represents how the data was generated. Okay, I think that's what the lesson is. All right. As for the last part here, let me get rid of this here. As for the last part here, we're going to create a new variable called mu, which is the expected value of y squared. Okay, so notice that that this mu is different from this mu. Okay, because this mu will actually be a squared value. That mu is, it's the square root of a squared value. So those shouldn't be confused. And we're going to regress it on the systematic component, x1 squared plus x2 squared minus 1, and then use t-test to confirm that the parameter estimates support Pythagoras' theorem. Okay, good enough. So, so we need to create our variable mu, which I'm just going to put as y squared. Okay. And then we fit it against this systematic component. This little -1 says to remove the intercept that is otherwise automatically added when we use, our LM function. Why are we removing the intercept? Well, because Pythagoras' theorem doesn't have an intercept. It's just, side 1 squared plus side 2 squared, and then take the square root. Okay. So, so I'm going to fit this. So I fit this. And so here's our, our estimates. Notice that if we were just, looking at p-values, there isn't really anything to suggest that this model, which again is the data, well, very close to the data generating process, looks very similar, or at least in terms of significance values, to the one that we know does not represent the data generating process. All right. So, but anyway, so we see that that this might be a good fit to the, or this might support Pythagoras' theorem, because Pythagoras' theorem means that x1 squared plus x2 squared, that both x1 and x2 squared, that they are very important to determining the hypotenuse, right? It's a deterministic relationship. Now, we might even go on to say which model is doing better, this one, or M0 or M0, which again did not represent Pythagoras' theorem. Okay, and so so I'm just going to use AIC for the two models, and before I do that, I believe that this is okay. Usually for AIC, you want to make sure that you're using the same data, and here we're using mu, which is y squared, instead of y. But because it's directly derived from y, I believe that this is okay. But if you know better, then please tell me. But if we do AIC here, okay, we see that M0 is apparently doing quite a bit better. Is doing quite a bit better than the data generating process. This makes me think then that you cannot compare these two models with AIC. I'm just not really sure. But anyway, I could come up with the rationale as to why you shouldn't be able to do it, but I'm not sure. But if anybody knows, then please let me know. Okay, bye.